here we have the linear systems that we arrived at. There we have used the boundary conditions. But if we use the boundary conditions as separate equations, then we can also formulate the whole problem in this way. So, for example, here, that is in the PEW formulation, we have introduced then the phi 0 as the boundary condition. So the phi 0 is a new variable that we have to determine, and this determined by the boundary condition phi a. So then we don't need to change the source term because that is taken into account by the minus AW phi 0. Likewise at the right boundary. So by that we introduce two more unknowns which are determined by the boundary conditions. In the index notation we would get in this system. So we have still a tridiagonal system, but we have two unknowns more. So we have an nj by plus 2 by nj plus 2 matrix. So it depends on how you like it. So we have discussed this. So, and well, this is the value factorization that you can also read then in the course notes, in the lecture notes. But we want now to look at the treatment of Neumann boundary conditions. After we have seen how to do it with directly boundary conditions, we want to see how we can treat Neumann boundary conditions. So we assume that now, we suppose that the left boundary condition is the following. So that left boundary condition is the following. Let's see, I think we have now 23. That the derivative of phi with respect to x at xa is equal to some slope, phi a prime. So the phi a prime is just some slope, some given value. So we assume we have that slope. So that is just a value. So if the slope is given, the d phi dx, then we call that a Neumann boundary condition. The Dirichlet boundary condition, the value itself is given. So let us take an example. The example is the 1D steady heat equation. And that is then the following. That is 24. We have no time derivative, we have the velocity 0, we have just, and now I write it in differential form, the ddx of the thermal conductivity times our variable is here now the temperature. So here we have then the heat conduction, and we have a source term, S of T. And now we assume that this heat conduction has the following boundary condition. So we assume that the heat flux at the left boundary is given. So, and that means that we have given, that is then 25, the heat flux is Q, and I write it with A because it's at the left boundary, and the heat flux is minus thermal conductivity times the derivative of the temperature, and that is then taken at XA. So that is known. An example would be simply adiabatic, when we have an isolated left boundary, that would be 0. But we could also have given some heat flux, then this value would be known. So So then, if we apply that to our steady diffusion equation in the integral form 5, we would then have the diffusion coefficient would be the thermal conductivity, and our variable that we are solving for would be temperature. So then we get for this, in the first control volume that is next to the left boundary, the following. That would be 26. That what we need to compute there will be the flux, the heat flux over the left boundary, and we will compute that as minus K times the area times the derivative of the temperature at that western boundary, which is the left boundary of the domain, XA. And you see, this is very nice because we have it given here. If we multiply then the QA by the area, we have this quantity. You see, minus K dt dx at XA is exactly what we want, because that is at W, at the left boundary, western boundary for the first cell. So this is QA, the given heat flux at the left boundary of the domain QA times the area. And from that we can then get the finite volume method, then for the first control volume. So the finite volume method for the first control volume we get that then from the approximation of the integral form of the steady diffusion equation, and that is equation 5. And there we have to approximate the flux, diffusive flux over the eastern phase, and that is unchanged. There we have no change. That is the thermal conductivity times the area times the approximation of the derivative dt dx, which is then Te minus Tp divided by the distance between P and E. And then we have minus Ka dt dx at the western phase. And we see this is QAA. So we use then here what we have here. So we use here 26. That is the heat flux over the western phase that we need here is QA, the given heat flux at the left boundary, times the area A. And we use the source term. And there we use this linearization with the uniform part plus the part that is depending on the solution. And our solution here is then Tp. So you see, here we use the boundary condition, that these are equal. So here we use then we have used 26 to get this. And then we can order the equations again as usual. We take the parts that depend on Tp to the left and the rest to the right. And then we get the following. So from the left we take this over. Then we get the thermal conductivity at the eastern phase divided by the distance between the grid points P and E times the area. This stays on the right hand side, this is known, but we get from the source term, we get the SP on the left hand side, and that is Tp. And on the right hand side, we will have the contribution from E, and that is then the Ke divided by the distance between T and E times the area times the temperature E plus the terms that are constant, and that is then in our case the QA coming from the heat flux boundary condition plus uniform part of the source term. So then we can identify again these coefficients. So this would be the coefficient AP, this would be the coefficient AE, and we could call this here as the modified uniform part of the source term SU tilde. We could also introduce, if we like, AW, that would be 0 in that case, if we would do that. So then we get from this then the following equation. So from this we get then the following equation, it would be 27, that we get AP times TP is equal to AE TP plus this uniform source term containing the boundary condition. And as I said, this corresponds actually to the general form that we have for the interior cells 13, where we also have the AW, but in this case the AW is simply 0. So then, and the form of AP is the sum of AE and AW minus SP is still true. Okay, so, and that if we write it in index form, then we would get the following. So that can say this equation 27 can also be expressed as the equation 17, that was the index form. That would be here, we would then get 28, we would get the A1, T1, and then we would bring that on the left-hand side, C1, T2 is equal to the D1 tilde. If we use then the following equivalence, where C1 would be corresponding to the minus AE, and let's see, and that would be let us write that first, minus AE, and that would be in our case the minus thermal conductivity at 1 plus 1/2, that is the eastern cell for index for the cell number 1, divided by the distance between nodes 2 and 1, and the A1 that would correspond to the AP, and that would be minus C1 plus S1. S1 is our SP. So S1 is SP. That is our coming from the source code. And the D1 tilde, that would be the SU plus QA times the area. So that would be our SU tilde. SU tilde. So then we have the correspondence. So then we would have to change, as we see here, the C1 is unchanged. What we would have to change with respect to the general formula is the A1, because we do not have the B1 appearing here. And we would have to change the D1 tilde, because we have here then not the boundary treatment as for directly appearing, but the boundary treatment with the heat flux. So they would have to be changed. So that means, we can write that, thus, let's see, we would have to change A1 would have to be changed, and D1 tilde have to be changed compared to 17. I think 17 was the directly boundary treatment for the first cell, actually. So, then you see, in this formulation, we don't need the temperature. The temperature doesn't appear here, if we do it like that. We only need the heat flux. That is a natural quantity, this is our diffusive quantity that we need, and it comes in by this boundary condition in a natural way. If we want to know the temperature, anyway, we can get it by a finite difference approximation. So the remark is that let's see, this boundary condition, that is the boundary condition, let's see, yeah. So that is the TA with the Neumann boundary condition, I think it was 25, does not need to be computed. So you see, it doesn't appear, because the natural quantity is actually the heat flux in this case, which is given. If we want it, so if you want it, it can be computed, can be TA, can be computed from the boundary condition, actually. That is from 25. And the boundary condition was that the QA is minus K times the dt of XA dx. That is the boundary condition. And then we approximate this derivative by the finite difference approximation. And this would be, in our case, the temperature in the cell 1 minus the temperature at the boundary that we want to determine, divided by the distance between the grid point 1 and the left boundary XA. And then, when we have computed the T1, we know our coordinates of the grid points of the boundary, we know the thermal conductivity, the heat flux is given, then we can solve that for TA. So then, the result is then that the TA gets equal to, now if we take here an equal sign, is then T1 plus the distance between grid point x1 and left boundary XA times the heat flux divided by the thermal conductivity. So then we can compute it in this way. So the catch is using the boundary condition and approximating the derivative, the TDX, by the finite difference approximation. So, then we know how to do that, and you can do as an exercise to train that yourself. Treat the boundary condition at the right boundary, QB, where the heat flux is given at the right boundary, so minus K thermal conductivity dt dx is given at the right boundary xb. So treat that, do the same approach so that you can see how the last row of the system of equations is changed compared to the Dirichlet boundary condition. That was number 20 that we discussed. You will get something similar. So now we want to look at some special cases. So after we've seen the Neumann boundary conditions, we want also now to see other cases. And the first now is treatment of nonlinear diffusion. So we have mostly now assumed that we get linear systems where the diffusion coefficient is independent of the unknown. Now we want to see how we do it when it is dependent on the unknown. So, treatment of nonlinear diffusion. So, we suppose now that that our diffusion coefficient is dependent on the solution phi. So then the systems of equations that we get are no longer linear, but nonlinear. That is either with the PEW form or with the index notation. These systems are then nonlinear. They are nonlinear. So the example would be, again, continuing on the example that we just had for the heat flux. We would have then K equal to K of T in the steady heat conduction equation. So how can we do that? So then we have to guess. We have to have an initial guess on the temperature to compute the thermal conductivity. So we have now, step one will be we guess the temperature, T 0. So that will be now the superscript that will now indicate the iteration. We do that at all grid points, and that means that we, for example, let's take an example, e.g., that we say that the Tj, the initial guess, is 0 for j from 1. Usually you would take more intelligent choice when you know the boundary condition, but that would be one way. You could also then introduce the values at the boundary, so the value at the left boundary that gets the index, the subscript 0. So the initial guess for that, you would take, if we have Dirichlet boundary conditions, you would take the given boundary temperature there. And for the value that you have at the right boundary, which would be nj plus 1, initial guess, you would take, if we have Dirichlet boundary condition, the temperature there. So then we have that, and then the next step would be that we compute our thermal conductivity wherever we need it. So compute the KW and the KE for all nodes or all cells P. So that would correspond, or we would compute the kj plus minus 1/2 for all j. Using the latest with the t nu. The nu here, that is equal to 0. So that is, this index here is the iteration index. Because we need that, because we have to go back to this step here. And then we can, by that, compute the coefficients. So we can compute the coefficients, that is the AE and AW and AP and so on, in 11 or in 12, depending whether we use the PEW notation or the index notation. And then we have a linear system, because everything depends on the old iteration level. So then we solve this linear system. Solve, and we get the system that we had discussed, the tri-diagonal, and then it is linear. That is important. System, and that is then A times the unknown vector t, and that is then equal to the right-hand side d. And the A here is then depending on our iteration nu. And the solution of that, we call that then the new iteration. That is then the value, we call it t nu plus 1. So solution that we get by solving the tri-diagonal linear system, that is then t, and we call that t nu plus 1. And as I said before, that we note that the A is a function of the old iteration. Therefore, this is linear. So A is known. A is constant in that sense. And then we solve for t, and then we get that. And then the next step is that we check whether we have convergence. And that we do in a similar way as we also do in the present assignment 7. We have done it previously. Say in this case we would check the new iteration value minus the old iteration value. And for example, we would check it with a 2 norm. You can use any other. And we would then have here some tolerance. And we would check it against the change from the first iterate, from the initial guess to the first iterate. So then we could check that. And this is then some tolerance. So tolerance, so that is some tolerance. That is, for example, as we use now in the current exercise, we have a 10 to the minus 6. It depends on the problem. But that will give you then a criterion to stop the iteration. That's our stopping criterion. So that means we stop. In that case, we have an iteration. Stop the iteration. If that is fulfilled. So if that is fulfilled, we can continue the sentence. So if that is fulfilled, stop the iteration. And we accept then as the solution to our problem the latest iterate, t nu plus 1. That is then accepted as the solution. And if it is not fulfilled, this criterion, so if the stopping criterion is not fulfilled, and usually I would also recommend to have nu smaller than some nu max, so that you decide on a maximum iteration. It's also problem dependent. If you would have an even iteration, that might be even of the order of 20. It depends. Then a set new, so in the sense of an assignment in the computer language, equal to the new plus 1. So that is a variable assignment that we have here in the computer language. For example, in MATLAB, the simulate Fortran, whatever you like, and go to the point 2 above. So then we compute again then the coefficients with the latest iterate, and solve again the system, check the solution, whether the iteration is okay or not, and we do that until this criterion is met. If we happen to not to meet the criterion, that we need read mu max, then we can just note that it has not converged. So then we just have to check that and see what is going wrong. We might need more iterations, or there is some fundamental problem that has to be checked. But this is then a way how you can treat non-linear diffusion. That is then doing iterations. But in any case, the costly step is this one. The costly step is the solution of the linear system. And that is important to remember. The solution of a tridiagonal linear system with the Thomas algorithm takes about 8 times the number of unknowns operations. If we have nj unknowns, it needs about 8 times nj floating point operations. So that is something that I think one should always keep in mind when we talk about that. That is the cost of a linear system, 8 times the number of unknowns. It's linear, that is the good point. So now let's continue and look at the treatment of the source term. If we have a case where the source term might destroy diagonal dominance. So we look at the case when we use our source term approximation this is the integral appearing in the integral form of the steady diffusion equation. So the mean source term times the volume of the cell, this is the source term appearing there. And that is approximated, in our case, in a linear way by the uniform part of the source term some coefficient Sp times phi p. And we want to investigate here the case when Sp is positive. Why is that the critical case? Because the AP looks the following. So the AP, remember, that was our derivation, is equal to the coefficient in W plus the coefficient in V, that is the western and the eastern cells, minus the Sp. And if this is positive, this will weaken the diagonal dominance. So we might lose diagonal dominance. If this is negative or 0, by this, if it's 0, it is just the same as there is no problem with that. We get equal because the AW and the AE, in our case, they are positive. And if this is negative, then this will give us something positive, and we will get even more diagonal dominance. So if this is negative, it will just be good. But the problem, if it's positive, we might lose diagonal dominance. So we have to check whether the absolute value of AP is smaller equal the absolute value of AW and AE. So this is then the AW plus the AE minus SP. And then we have to do the distinction, and here we use now that the AW is greater equal than 0 and the AE is greater equal than 0. They contain the diffusion coefficient which is positive, the area and the distances, they are all positive. They might be 0. And then we have the two cases. Either we have that this is positive, then we have the AW plus AE minus SP, and that is then the case when this is positive. So that is the case if the AW plus AE is greater equal than SP. So then this is positive and we can remove the absolute values. In the other case, we have to change the sign and we get SP minus AW plus AE. And that is if the AW plus AE is smaller than SP. So then we can lose diagonal dominance in this case. So diagonal dominance, that is then that we need 30. In this case, we need that the absolute value of AP has to be smaller equal than the modulus of AW and the modulus of AE. That is the diagonal dominance. And that is violated. So it's lost. And then you can check that yourself when we have these conditions. SP smaller equal AW plus AE. And for AW plus AE smaller SP and smaller than 2 times W plus AE. So we have a situation, you see here, that SP essentially when it is between 0 and this 2 times the sum of AW and AE, then it is lost. So then we can no longer use a TDMA, but we must do it differently, and we can do it actually still with a TDMA with a little trick. So to guarantee the diagonal dominance, we solve our systems. Let's see. I think it was. Now I have to check my numbers here. I think it is. Let's see. Well, it's our linear systems. So if, here you might check the numbers, but it's the main is the linear systems that we are solving here. So we solve these linear systems then not just as we have defined them originally, but we solve them iteratively with the following trick. We put now the critical part, and the critical part is now our SP phi p. We put that into at the old iterate, and then it is constant. So we leg that in the iteration. So we put that SP as phi p as the iteration new. And then we don't have any contribution SP, because that is then 0. So the SP in the matrix is 0. So because it is then taken into account here. But the price for that is that we have to do it iteratively. So we have then to put this part that is dependent on the solution into the right-hand side at the old iteration. We do an iteration, we update, but then we can keep the diagonal dominance. That is the trick. Okay, well, then I think that's what I wanted to say. So that means we can now treat Dirichlet boundary conditions, Neumann boundary conditions, we can treat nonlinear diffusion, and we can treat source terms. And the source terms, as I said before, if they are negative, if they have coefficients that are negative or 0, then it is not a problem. If they are positive, then we can do this treatment. An alternative would be to keep it on the left-hand side and to use something other than Thomas algorithm. That would also be an option. But this is then an option where you could still use the Thomas algorithm, but at the price that you would have to do iterations. If you have a nonlinear problem, you'd have to do it anyway. Then it is not a big deal. But if you would have a linear problem, it would be really a disadvantage, because then you would have to do a couple of iterations for this in order to be able to use the TDMA. Because with this trick, the SP doesn't appear in the matrix, and so it doesn't appear here, and it doesn't destroy the diagonal dominance. Okay, so then I remind you again of the Fortran introduction tomorrow. That is then in Part 4 and 18, 15 to 20. And you can also, if you like, try to get hold of some Fortran manual. You can look at this homepage. There are some links. You can download Fortran compiler. You might already have it. If you have a Linux, for example, usually you get it with that. Otherwise, you can download it. And, well, I think that's it.